Hello and welcome to this new section of the course. We'll be looking at numerical methods in this chapter here. We'll start by looking at locating roots, looking at iterations and Newton-Raphson method and applications of numerical methods for modeling real-life situations. I'm so excited to share my knowledge with you here. Let's look into it. So, for the first example, I'll challenge you to pause the video for about a minute or so and try to see whether you can solve this equation or not. Okay, pause the video and have a go. Right, okay, welcome back. If you did try to solve it and you didn't manage to get a solution, that's fine. I I commend your work and your attempts. That's fine. But this sort of a situation is an example of a problem where we do not have an algebraic solution. No matter what you do, whether you take e of both sides, you end up with e to the power of e, or if you take logarithm of both sides, you end up taking log of a log. So, finding an algebraic solution to this problem is not so straightforward. But I have good news for you. It does have solution. In fact, it has more than one solution. If I show you the graph of the left side of the equation here, if we call e to the power of half x minus 2 one function, this is the graph for that part. And if I plot the graph for logarithm of x, you'll see that these two curves intersect at exactly 2 points. But how do we go ahead and actually solve such problems in real life if we had to solve them? Well, the strategy, in a nutshell, is to bring everything on one side of the equal sign. We can rewrite this equation as e to the power of half x, take away 2, take away log of x. This means that the right side of the equation will equal to 0. Now, this is not the only way to write it. We could simply multiply everything by -1, and we could have written logarithm of x, subtracting e to the power of half x, and adding 2, and that would also equal to 0. There is no right and wrong way to get either this solution or that solution is valid. Now, I'm not calling it a solution. I'm saying these two are two forms of rewriting the same equation again and again. Now, we can go ahead and plot this function. If we call this a new function, let's say g of x, and plot that on a graph, what we end up with, this green line here. So this green graph or green curve here is the equation when we have equated one side of the equation to 0. And what you notice is that where the original two equations intersected coincides exactly with where this green curve has a root. Root means that it's crossing the x-axis, right? And this intersection point is exactly where the root of the green line lies. So that's why in the first section of this course we'll be looking and to locate roots of certain functions. Now these functions come from equations that we may find difficult to solve with algebra or with algebraic techniques. Let's look at this first example here. The diagram shows a sketch of a cubic function, and we are asked to explain how the graph shows that f of x has a root between 2 and 3. Well, we can see graphically that the graph crosses the x-axis at some interval between 2, and 3, right? So since the graph crosses the x-axis between x2 and x equaling 2 and x equaling 3, that is where the root must lie. So that simply answers part A of this question. So in part B, we are asked to show that f of x has a root between 1.4 and 1.5. How can we do that? We substitute these two values into the original function itself. F of x was a polynomial of third degree. So we are going to substitute 1.4 in that equation and we end up with a positive value. When we substitute 1.5 in the same function, we end up with a negative value. And that's not surprising because we evaluated the function at some point to the right of the root and at some x value to the left of the root. So it's not a surprise that one of them is positive, one of the answers. This change of sign is in fact enough to show that we have a root between 1.4 and 1.5. Let's look at the next part. Right, there is a generalization that we can make here. Looking at this negative cubic curve, we know that in the interval of a to b, we have three roots, 3 points where the graph intersects the x-axis. Now, every time you have three roots, you will have a polynomial to the odd power. Okay, so comparing comparing a and b, there is change of sign at three different points. Okay, now next graph in the middle of the page, we have a and b that have no change of sign. So we have to be negative and b when when evaluated at this x value, we will get a negative answer, and when evaluated at this x value, we'll get another negative answer. So what we are generalizing is that when we have no change of root, we may have in fact even number of roots. So that is a generalization that we can make. We may have two, we may have even number of roots. We may have four roots, or we may get six roots. Okay, if we have a graph of a quartic equation, we may such situations with four roots. Okay, so if we evaluated this graph at this point and this point, we may not see a change of sign. We may see two negative values. Okay, so the generalization was that when you do have a change of sign at A here, we evaluated xa, and at xb, we evaluated the function to be at xb, the result of xb. So when you have a change of sign, there may be one root, there may be three roots, there may be five roots or more. The answer, the number of roots will be odd. And there is another generalization that we may have to take. There may be a change of sign, but there may not be a root at all. Zero, after all, is an even function. Get another example. In this example, we've been told that the graph of a function is cubic curve, and student observes that f of 1.2 and f of 1.6 are both negative. State that f of x has no roots in this interval. The student states that there is no roots in this interval. Explain, referring to the diagram, why the student is incorrect. Looking at the diagram here, there are in fact three roots between 1 and 2. 1.6 is somewhere in the second half of the graph, and 1.1 is somewhere here. So we know we can evaluate that the function at these two coordinates and show that there is a change of sign. So let's do that. We are going to substitute 1.1 into this equation, and we can do that at a later stage. So if there is no change of sign, there could be no roots. There could be possibly either 2, 4, or 6 roots in that interval. So if both of those answers come out to be negative, looking at the diagram, they, the fact that the student came up with the function to be negative at either end is because possibly he evaluated or she evaluated the function at these 2 points, and they were both negative. The fact that they are both negative means that there is either 0, 2, 4, or 6 roots, or even more number of roots. So yes, she could be right. There could be no roots, but there could be an even number of roots. Okay, so as we said from the diagram, we know that in fact the cubic has 3 roots in the interval of 1 to 2. In the next part of the question, we are asked to calculate f of 1.3, f of 1.5, and f of 1.7, and use our answers to explain why there is at least 3 roots in this interval of 1.1 and 1.7. So what we're going to do is simply substitute those values into the polynomial, and we get change of from negative uh, in the first part, we end up with a positive answer for 1.3, and we see that the function evaluates to negative again. So there is at least 2 change of signs, and in fact, putting 1.7 into the function, we get yet another change of sign. So this change of sign means there is one root here, this change of sign is another root here, and another root in this interval. So there are 3 intervals where we can focus and zoom in and find to greater granularity. But we are not quite asked to do that yet. Let's see the next part of the question. So in part C, we are given that the root of f of x is alpha. We are to show that alpha is exactly 1.753 to 3 decimal places. Now we are supposed to go into greater depth. In the next example, we've been given the graph of log of x and graph of 1 over x. We were asked to explain how our diagram shows that the function log of x minus 1 over x has only one root. From the diagram, we can see the two curves intersect at one point. So when these two curves intersect, the point of intersection would be where f of x here has a root equal to 0. If I jog back to your memory to the first diagram I showed you in this chapter, we have written the two equations on one side of the equal sign, and we've subtracted one from the other. Therefore, where this f of x is equal to 0 would be the point where we would find the intersection point of the blue line and the red line. Rearranging f of x, we can see that that is the intersection point where the graph, these two go to each other. The next part, we are asked to calculate and show that the root lies between 1.7 and 1.8. So we simply substitute those values into the function f of x, and we see a change of sign. The change of sign is enough to show that the root lies within this interval. In part C of this question, we are asked to show that the root alpha is 1.753 correct to 3 decimal places. So, what we need to do is pick a number that is slightly higher than alpha and pick a number that is slightly lower than alpha and substitute those two values, those two numbers into function itself. So we see on the number line that the root the question told us is in the middle. We are going to pick these two values and evaluate the function at those 2 points. If we see a change of sign, that's enough to show that there is a change of sign. There is a root between at alpha being equal to 1.753. So, and correctly, so we see that there is a negative answer on the left and there is a positive answer on the right. So the root in fact does lie between those when x is 1.753 correct to 3 decimal places. Notice we took exactly 0.0005 away from this number and we added that value to that number alpha, to the number alpha. Okay, so I'll see you in the next example and next section.